Okay. So last time we finished on discussion of state graph of a monitor. On the bottom, you see the scheme of a monitor from Wikipedia. It is seen from the perspective of the process which states are given in the graph. So it is green cycle, the green circle, and red circle is, or sometimes pink, because there are situations in which we discuss more than two processes. There are other processes. Out of monitor means that we have a process that operates in external code to the monitor, and in some moment the process enters the method of the monitor, which is begin in our code with P. It is begin with closing the critical section of the monitor if it is free, and the process becomes active in monitor. Let's look how it happens. The process simply enters the monitor. The second transition is the same operations from the perspective of the process, but critical section is occupied by another process. So our process becomes ready in monitor. It waits for the critical section. This is such situation when our process wants to enter, but critical section is already occupied. Next transition is suspending the process. The operation wait on a condition. In this example, it is CI, condition number I. The process becomes suspended on condition CI. It waits in this side chamber for resumption. Other process signals the condition CI. Our process can return to the critical section. This is illustration of that. We can say that the processes exchange in the critical section. The red one executes signal and frees the critical section and gives this critical section to a process waiting on a condition. However, if there is more than one process waiting on condition CI, one of them is resumed, and the rest are still waiting. This shows this situation. We had two processes in waiting on a condition. One of them is resumed, but it is not our process, it is red, and our process still waits. This was signaling a condition by another process. Underlined is invoked by another process. Here is what happens with our process when it executes signal on condition CI. It gives critical section to one of processes waiting on a condition variable. When other process leaves the critical section by executing wait on a condition or leaving a monitor, it frees the critical section, so our process can enter. These are two situations: red process waits or pink process leaves. In both situations, our process can enter the critical section. However, if more than one process waits for a critical section, only one of those processes is led to take the critical section. So we have four processes. Once more, four processes. This is the alternative. A process waits or leaves the critical section. The process, one of processes waiting to enter, enters, and our process still waits to take the critical section. Of course, a process to enter the critical section is chosen non-deterministically. When our process executes, leaves the monitor, it comes to the state out of monitor, so it is just leaving a monitor and freeing its critical section. Here we have illustration that we can have many conditions in a monitor, and we have separate suspended states. On every condition, there is a separate state for suspending processes. Here we have the differences in Brinkhausen monitor. Those differences are, some of them are just another naming, like instead of conditions we have queues. It is just terminology. But we have no direct resumption in the Brinkhausen monitor. So how to guarantee that the resumed process will get the critical section first? For this purpose, it is additional state called notified. The state notified is for process that waits that waited on the condition. It is not waiting anymore because it is resumed by other process, but it does not get immediately the critical section because the resuming process does not leave the critical section. It continues in critical section. So a resumed process becomes notified. In this state, it has privilege over other processes that want to enter the critical section. To have it successful, we must have at most one notified process. We cannot have two processes in notified state, because the problem would return which of those processes should be resumed. So only one process can be notified. Therefore, after resuming a process, we cannot, the resuming process cannot signal another process. Only one can be signaled. And for the same purpose, the resuming process cannot wait after resumption. It can only leave the monitor. Let us look at the state of the graph of states. Here I did not prepare an animation. So let's look. Out of monitor process, when it wants to enter the critical section, it executes, it starts the sum of one of the methods of the monitor. When critical section is free, it becomes active in monitor. It is the same as in whole monitor. And if critical section is occupied, the process becomes ready in monitor. It is the same. Here we have queues instead of conditions, so we execute wait on a queue, and we become suspended on this queue. It is a counterpart of operation on a condition variable. But if another process executes continue, it has a different name. In whole monitor we have signal, in Greenhausen we have continue. But the meaning is similar. But the process does not enter the active because resuming process does not leave the critical section. It still occupies. So our process stays notified. When other process, this one, which resumed our process, of course, executes NV, which is leaving the critical section, the notified process becomes active. If a process executes wait on, it should be Q, not SX. It should be QX, because there are Qs in Bringhausen monitor. Okay. Executes, and here as well, it is QX. If a process executes wait on a queue or leaves the critical section, but there is no notified process, a process that is ready can become active. If there is notified, it has privilege over ready. And if there is notified or there is more than one process waiting on in ready state, the rest continue to wait. When the process leaves the monitor, it becomes out of monitor, and similarly to whole monitor, we can have many suspended states. For every queue separate state. And finally, the continue operation executed by our process. Oh no, it's not the true. It shouldn't. If the process executes continue, it stays active in monitor. It is an error here. So it's online debugging. I will repair this state graph. I invented this graph by modification of the previous one. That's why I didn't take care on everything. Okay, and here we have continue. I will let us let us do it horizontally. And this arrow is non-existent. Okay, and I will prepare animation later because probably it occurs in, it is static. It should occur in that moment. Okay. So active process stays to be active only if it executes wait. If it's active and executes continue, it stays active, but wakes up one of processes suspended on a queue. Okay. This is the Wikipedia interpretation of Brinhansen monitor. And I added an animation to this scheme. When a process wants to enter the critical section, it looks at the inside the monitor. If critical section is free, it takes the critical section. If a process looks at the critical section that is occupied, it waits on entry to the monitor. When a process waits, it can let another process to enter the monitor. And when the process executes or not signal, it is called continue. Okay. If it executes continue, it notifies the process that waits on a semaphore, and it enters the waiting state for a critical section, but this exclamation mark shows that it waits with privilege. Another process can enter the ready state, waiting for critical section. If the red process goes out of the monitor, the notified process enters the critical section with privilege over other processes waiting. Okay. This was all about monitors. Today, you will have the lecture of Mr. Grabski of some practical aspects of synchronization. So my suggestion is to attend this lecture, and you can ask the questions to Mr. Grabski, because you have two exercises on labs in synchronization. So it is very important to understand the synchronization to pass labs. Okay. Another means of synchronization, we learned two of them. It is semaphore and monitor. Another means is messages. In semaphores and monitors, we need common memory. In semaphore, it is the value of semaphore that is common variable to the processes. In monitor, internal variables of a monitor and condition variables are in memory common to the processes. In message passing, we have no common memory. We can only exchange messages between processes. And the synchronization is based on the fact that message cannot be received unless it is sent. And we have two basic primitives. Primitives are system calls concerning message passing. They are send and receive. And we have special part of operating system called message passing system that collects messages from other computers or the same computer, because we can send messages between processes on the same computer, and it delivers the messages to the recipients. There are two paradigms of message passing. One paradigm, but two versions: synchrony or asynchrony. Synchronous primitives concern if a process that calls a primitive waits for completion of this primitive or continues if the communication cannot take place. So on the sender side, synchronous send means that we send a message and we can continue if we know that the recipient received the message. It is synchronous. Asynchronous means that we send a message and continue without looking if the recipient got the message or not. On the recipient side, synchronous primitive, synchronous receive primitive means that we call receive. If a message is ready, we get it. If not, we continue without getting this message. It's asynchronous receive. Synchronous receive means that if we call receive and the message is not ready, we wait until it becomes ready. It's blocking or synchronous receive. A special case is rendezvous. It is pair of synchronous messages sent forth and back. So a message is sent from the sender to the receiver, and the receiver sends back the reply. And both messages, the main message and the reply, are of synchronous nature. There are many versions of message passing. We will not deal with them because they are used mainly in distributing systems. That means that if we have no common memory, we use one of message passing protocols, and those protocols have many individual properties that we will not discuss in our lecture. We will show how processes can cooperate simply. They can build a buffer, like our buffer that we constructing using semaphores and monitors. But the buffer is held in a set of messages. So we can say that the buffer is volatile. It is somewhere in the air between sender and receiver. It has no memory like a vector or array. Just it flies in the air. In this solution, the messages have permanent the messages are permanent. That means that if we create a message, it flows forth and back between the parties, cooperating parties, but it is not discarded when it is received. It still has some manner of being. Let us define the size of the buffer and the producer process, how it operates. It produces an item and sets an item entered to the message. Let's look how it happens. While true, so it is infinite loop. The producer creates an item. It receives an empty message, M, from the consumer. It enters the item to the message and sends the message back to the consumer. On consumer side, we have similar item and message and a loop iterator I. And for n times, the consumer creates empty messages. They will serve as a means for creating a buffer. So it sends n empty messages to the sender. And in infinite loop, the receiver receives a message from the producer, extracts an item from the message, and sends back the message to the producer. Okay, this was the example of using messages, but we will not use them. And in our midterm and final exam, you will not have an exercise of messages. Instead, let us look at two examples of exercises for synchronization on semaphores. First is so-called concurrent problem with writers and readers. The idea of this solution is that we have a database, DB. DB is here a semaphore. So database is something to which we can write on read. So we have operations write database and read database. They operate on the database. And the assumptions are you saw the danger of modification of common variable by two processes. It was the first example in our lecture with global variable that was incremented and decremented. So we cannot allow to concurrently write to the database because it can raise an error in database. So two producers, two writers, cannot write to database at the same time. So the database is a critical section between them because they cannot enter writing together if there are more than one. The same exclusion is between writing and reading. That means when we write, we cannot read. When we read, we cannot write. It is exclusive. It is the second assumption. And third assumption is that readers can read in parallel. It means that when one of the readers started to read, we can let other readers to read freely, but we exclude writers. Okay, so for access to database, we have DB semaphore, and every writer executes P on DB when it wants to write, and VDB after writing. The same in reader. P of DB when we enter reading, V of DB when we finish to read. But how can we know that more than one reader reads. We need a counter. So we have a variable RC, which is reader count, that holds number of readers that currently access database. So before entering to read, reader count is incremented. After leaving the database, it is decremented. But if we have a counter that is incremented, we must protect this variable from concurrent access, because we know what can happen if we modify a variable without some protection. So we have mutex binary semaphore that takes care about reader count. Reader count is preceded by P and followed by V, and again preceded by P and followed by V. So it is this from P to V, those two sequences are critical sections from the perspective of reader count. Let's look how the consumer operates. It closes the critical section of RC, increments RC if it is a change from 0 to 1, from no reader to one reader, we take the critical section. We execute P of db. And we leave the critical section of RC. Here we access the database, maybe concurrently with other readers. And after reading data, we execute P of mutex that governs RC. So after that, we decrement RC by one. One process less reads the database. And if we are the last one, which means that reader count changed from 1 to 0, here, we unblock access to the critical section. And finally, we leave the critical section of reader count. Here we have the constructor of this class. We initiate mutex to 1 because initially the critical section of variable RC is free. We initiate db to 1 because initially no process accessed database, and reader count is 0. These are the initial values of those variables. Now let's look. One element looks strange. Because there is P in critical section. It is similar to the situation which I showed you as a deadlock. It was in an example of a circular buffer. So it was subject to deadlock. So we changed the order of operations to protect this system from deadlock. Here we have something similar. We close the critical section of mutex that governs RC. Here we conditionally, but we stop on DB semaphore. And finally, the critical section is unblocked. So is it safe or not? Here it is safe. Why? Because there is no mutual relation between writer and reader on this critical section. So P is executed inside the critical section, but V on this semaphore here does not require to enter the critical section of mutex. So this solution is correct and safe. It has no deadlock. Once again, because P is executed inside the critical section, but unblocking the process after P here is not executed in this critical section. So a process can freely enter the write method in which it can unblock our process. So it is safe. But this solution is dangerous from another point of view. Let's look. If we increment reader count, maybe several readers entered this read procedure. Every one of them incremented RC, and it can happen that each time a process decrements reader count, some other process increments the reader count, and reader count never reaches zero. It is 1, 2, 3, 5, 2, 1, 5, 1, 2, 3, 4, but never zero. It can happen. So readers can dynamically block writers because V on DB in this solution is never called. Of course, it is an example of starvation. It is similar to the situation with philosophers, in which two philosophers, looking from the perspective of a single philosopher, its left-hand neighbor and right-hand neighbor, they put forks on a table, but never synchronously. They put it, put the forks in interleaving. If left fork is lying on a table, right hand one is taken, and reverse. When right hand fork lies on the table, left hand fork is occupied, and they are never both free. It is similar situation in which readers can successfully block the writer for long, very long time, maybe infinitely. So it is another example of starvation. And those two processes are called from outside when the writer prepares data and executes write, this procedure write, and reader reads data from the reader-writer class and uses the data read from database. It is this procedure read. The second example of using semaphores today is a problem for sleeping barber. I don't know what this name comes from. It is strange for me. Why it is called sleeping barber problem. For me, it is just barber's problem, not sleeping. I don't know why it is sleeping, but it is known in the literature under this name. Let's look. First, we discuss the assumptions. We have a barber shop, and in the barber shop, we have chairs on which the customers wait for a haircut. And they just wait on chairs. Of course, no more customers than chairs. The assumption here is that when the client enters barber shop and all chairs are occupied, the client leaves the barber shop without getting a haircut because the barber shop is too crowded. It illustrates a server that can be called several times for prepare some data, and it prevents the input buffer overflow or overloading the input of the server with the assumption that if we have two more calls, some of them are simply rejected and not served. So we prevent denial of service attack. The chairs constant informs how many calls we allow to wait, no more. If we have more waiting calls than we have chairs, we just ignore them. It prevents from overloading the input queue. Okay, when the barber comes to the barber shop, he takes one of the clients waiting on chairs and executes the service, which is haircut. This is pleasant solution because we do not assume how many barbers we have. It can be one or two. It can be then that sometimes more barbers come to the shop, for example, 5, and sometimes less, for example, 1 or 2, and everything works. Because we take from the chairs as many customers as we have free barbers. So simply a barber can come to the barber shop, give several services and disappear. And everything works correctly. Let's look at the variables. We have customers. This is the semaphore on which the barbers wait for a client. Because it can happen that a barber comes to the barber shop and no client is in. It can happen. Or there are clients, but there are less clients than barbers. So customers is a semaphore on which the barbers wait for clients if there are more customers than clients. Barbers is a semaphore on which clients wait for barber. So if we have more clients than barbers, they wait for haircut, but no more than chairs. Chairs is a constant, so we need not protect it from concurrent access. But for effective ignoring barber shop over the number of chairs, we need to count the customers that wait. So we have a waiting integer that holds number of clients that wait for haircut. Of course, if no client waits for haircut, this semaphore will be 0. Finally, we have mutex, a binary semaphore, that protects the waiting variable from concurrent access, because we increment and decrement this variable. Here it is decremented, here it is incremented. Okay, let's look at the operation of this barber shop. A client comes to the barber shop, increments number of waiting customers under mutex. Here it increments, but not over chairs. Not maximum is number of waiting equals to chairs. So if it is greater or equal to chairs, we skip over the entire operation and execute V of mutex. Here, P of mutex, if waiting is more or equal to chairs, we V of mutex. But if waiting is less than chairs, we increment number of waiting customers. We tell the barbers that there is one more customer to cut his hair. And we leave the critical section of mutex. So from here to here we have a critical section. Then we execute P of barbers because a customer must take one of the barbers to get a haircut. So it informs the barbers that there is one more customer, but takes one of the barbers. If taking the barbers is successful, the client gets a haircut. If not, the client waits for a free barber on this semaphore. Let's look at the barber. We take one of the customers. If there are no waiting customers, a barber just stays on this P operation. If it comes through this P, it enters the critical section of waiting, decrements number of waiting clients, and executes V of barbers because it lets one more client to take the barber. The client waits on P of barber, so we execute V of barber to take the pair of barber and client and start a haircut. And finally, V of mutex closes the critical section of waiting variable. Initially, the customers is 0, and every client that comes to the barber shop increments customers, but not more than 5. So this condition takes care about not more than chairs, not more than chairs. Barbers is 0. So initially we have 0 customers and 0 barbers. Every customer that comes increments customers. Every barber that comes increments barbers. Mutex is 1, it's typical mutex, and waiting variable initially is 0. Okay, so let us interpret the values of barbers and customers variables. If barbers is greater than 0, and customers is 0, that means that barbers wait for customers. If customers are greater than 0 and barbers is 0, the clients wait for barbers. They cannot be greater than 0 at the same time. We cannot have the situation where the barbers wait and customers wait. So either we have barbers waiting for customers, of customers waiting for barber, or a special case in which nobody waits. There are no customers, no barbers, and both semaphores, customers and barbers, are zero. If there are customers waiting, we cannot read the value of customers because typical semaphore does not allow to read the value of this semaphore. So not to read the value of the semaphore, we just count the customers. We have the variable waiting that informs us how many customers wait on chairs. Of course, not more than chairs. So if we have more customers than chairs, the number over chairs is just rejected. They ignore the barbershop. Okay. That's the end of our slide set for synchronization. However, I will show you some example solutions to the synchronization problems. Okay, let us call the notepad. What could be the first exercise? So, for example, some special form of semaphore. In a semaphore, we don't have any control over which process is resumed. An arbitrary process is resumed from a semaphore, if we call V. But if we want to have some control on an order in which processes are resumed. Okay. We will create a priority semaphore. Priority sem. Of course, it is a class of initial value I will use C-like notation. Okay. And of course, we have a variable that has a semaphore value, not int. Okay. How to stop the process if it wants to execute P on the semaphore that is 0? We need some suspending mechanism. Here, we will use binary semaphores. So we have binary semaphore waiting processes. Oh, let us give them initial values. Initial value. And we give 0 to this binary semaphore. Okay. Procedure. Oh, void. Void P. P operation has a parameter. If the process is with privilege or without a privilege. So operation P is with full priority. If semaphore variable is 0, we must stop our process. However, how to do this and leave the information about how many processes are suspended, because we need this information. Excuse me. So if semaphore value is 0, we increment some waiting count Oh, I forgot about one element. Of course, we need a critical section. So we need mutex, which is initial 0. And first we must execute mutex p. Okay. We incremented waiting count. We release the critical section. And we stop on the semaphore for waiting processes. When we are resumed, waiting count is decremented. Then we can decrement semaphore value and mutex v. Okay. Void v. Oh, v is without a parameter because v just resumes one of processes. Mutex p, semaphore value increment. And here we should distinguish between processes that are with privilege from those without a privilege. So it's not enough. We must have the waiting with priority and waiting regular. And we need waiting count for privileged processes and waiting count for regular processes. And here, depending on the priority parameter, we must do it such a way. If we have a priority, it is word count for prioritized and waiting on prioritized and word count from prioritize. Okay. And if we have no priority, we do the same with regular and regular. Oh. And in V, we first check if we have prioritized processes waiting, if word count for prioritized is greater than 0, we execute waiting prioritized V and P on mutex not to execute in parallel with the resumed process in critical section. Else, if waiting count for regular is greater than 0, waiting regular V mutex P. And finally, mutex V. And the constructor? Oh, constructor is here. All variables are initialized. Okay, so it's enough. So now we have a semaphore that treats some processes with priority, like if we call P with true, and other processes without a priority, they call P with parameter false. You can get such exercises that I call funny semaphores. You can get such an exercise in midterm or final exam. It is quite pleasant exercise to check if you understand some basic rules of synchronization. Okay, I will just send this solution on a chat of this meeting. Okay, and now let us do it using a monitor. Okay. We have semaphore value, okay. We don't have binary semaphores, but we have conditions. Of course, mutex is built in the monitor. And we have waiting with privilege and waiting regular. Do we need number of waiting? Of course. So we stay with those variables. Void P, of course, no mutex. If semaphore value is 0, if we have priority, waiting priority, wait, else waiting regular wait. That's all. Semaphore variable decrement. Okay. Void V. First, increment semaphore value. If we have, we need this variable, okay. So it is waiting count for prioritized increment, waiting count for prioritized decrement. Oh, here. And the same from regular ones. Okay. If waiting count for prioritize is greater than 0, waiting prioritized signal. Else is if waiting regular is greater than 0, waiting regular signal. And mutex is built in. So now you see that actually monitor solutions are more elegant and simpler. Okay. What else? What time we have? We have 10 minutes. Okay, so I will present you a problem that we will not solve today. We will solve it on in the next lecture this Tuesday, next week Tuesday. It's a problem of control over cars on road crossing. Let's call the word and create a picture. No. New canvas, okay. We have a crossing of not prioritized roads, so every car has the same priority, but we have the right-hand privilege rule. That means that if we have the possible collision, we give the priority to the car that is on the right. Okay, 4 or 2 roads, and we have the directions: north 0, east 1, south 2, and west 3. And cars can come from arbitrary direction. Let us take some icon of car. Do we have cars in this? No. Here. Oh, a car driving to the right. Oh, many pictures. Okay. This car drives, this car drives to the left. And we can have cars on every street, cars that approach the crossroads. And our goal is to let them safely drive through this crossroad using right-hand rule. So cars can go from north, from east, from south, and from west. And our role is to control the cars using the right-hand rule to safely drive through this crossroad. Okay, so you have some time to think about the solution, and I will provide the solution to this problem next week. Okay? So thank you for attendance to today's lecture. The next lecture is, of course, at school, and we will meet next week. Thank you and goodbye.
Thank you.
Oh, I will provide you the solution with monitor that is not in the chat. Oh, here we have the monitor solution to the problem of priority semaphore. Okay.